purpose of cooling load calculations, right? Okay, the primary objective of the cooling load calculation is to provide data required to design a HVAC system and to select HVAC equipment, right? The other guy is selecting equipment, right? Selecting equipments like fan call unit or AHU. Okay, so to select equipment, what you need input. Okay, that is what we are doing. We are trying to calculate the thermal load calculations. Okay, okay. If you go further down, you are going to understand what is the external load and internal load, right? So if you talk about internal load, you have a lights, ventilation, appliances. There are people. Okay, and if you talk about external load, you have a ceiling, roof, solar, window, walls, and the floor, right? So this is external load and internal load. Okay, so each and every load you have a sensible load and also latent load, right? Okay, and what is sensible load? It's a dry air. It's a dry air, right? And if you talk about latent load, it is a moisture air. Okay, so from the light, we know that there is no moisture, so it's only sensible, correct?
Only sensible, yeah.
And if you talk about walls or window, okay, or floor,
walls,
it is all sensible. Yeah. And if you talk about people normally you have there is a sensible load and as well as there is a latent load because when you breathe, it is a breath consists of both moisture, right?
Yeah.
Okay, so you have a sensible and you have a latent. Okay. And when you talk about outside air, it is having both moisture and
sensible and
moisture and dry air. So that means it's a sensible and latent. Okay.
Latent.
Okay. When you go further down, can you see that moisture removal and the latent load? Okay. So what is that external load and what is internal load and what are the types of the external load and what are the types in the internal load? Okay. Which one have a sensible and which one have a latent, right?
Yeah.
So that understanding you will get from here. Okay, when you go further down, this is the normal typical air conditioning system. Okay, you have an air conditioning system, you have a supplier, you have a returner going to the equipment, and then you have an outside air, right? Yeah. Okay, if you go further down, you will understand sensible cooling load and latent cooling loads, right? Okay.
Yes, sir.
Just now I have shared some video. There is a conduction, convection, and radiation. Okay.
Okay.
Yeah, if you see that conductive heat gains, right? It's a conduction from outside to inside through the partition by means of conduction. Okay, then infiltration through the gaps,
cracks and
cracks. Okay, then this is the occupant, this is the computer equipment, electrical lighting, right? So you have air conditioning machine. Okay, you have air conditioning machine which supply the cooling air and also it takes the warm air. So it is recirculate, right?
Yeah.
Okay. So the sensible load in the room and latent load in the coil, right?
Yes.
Because the latent load in the coil means the coil is full of moisture, right?
Moisture, it will condensate.
It will condensate. Yeah. Condensate. Okay. So when you go further down,
sir, one more thing, sir. This I had one doubt from before.
Yeah.
How the dehumidification part, like cooling, we are doing the temperature reduces. The dehumidification part, how we are controlling that?
Yeah. See, you have you have a two type of equipments. You have one is a heater, one is a humidifier, right?
Okay.
Okay. So the heater, what will happen? It will reduce the relative humidity by means of heater. Okay. If you want to increase the humidity, you can use humidifier, right?
Yes, sir.
Okay, so if you talk about some of the FAHU, okay, you have a enthalpy wheel, then you have a cooling coil, then also you have a sensible wheel. But still, after that also, you cannot able to achieve the required temperature. Then you will try to increase the temperature by means of adding heater. Right?
Yes, sir.
Okay, anyway, that we will study later. So that we will go step by step. Yeah, we will go step by step. Okay. Now, this is the weather. This is the weather conditions. Okay, so this weather condition based on ASHRAE guideline, right? Remember, I told you to study the ASHRAE climatic conditions.
Yeah, as per ASHRAE climatic condition. Yes, how to read the chart and everything.
Yeah. Then after that, understanding of U factor. Okay, what is a U factor? Say, for example, you have a thermal resistance through the different material having a different resistance. If you have a light material, that means you have a less resistance, right? If you have a more concrete, very thick material, then you mean you have a more resistance. If you have a more resistance, then whatever the hot air will not go through the inside through the particular material, right?
Yeah.
Okay, so if you have a thicker wall, your air conditioning load will be lesser inside, right?
Mm.
If you have a smaller wall, then your air conditioning load will increase because there is a lot of heat will pass through the your conduction wall, right?
Mm.
Okay, so how to calculate your U value based on the different material? If you talk about different materials having a different resistance, then when you add all the R value, you will get summation of all R value.
All the
Then yeah, U equal to 1 by R. Okay, so this will give you what is the U value, right?
yeah.
Okay, then when you
Having
go
more
for yeah,
higher U value is like it will increase the load.
it will increase the load. Yes, yes. Okay, that means less resistance basically, right?
Less resistance, yeah, inverse of
Yeah,
that.
yeah, yeah. So similarly for the U value for the roof.
Mm.
Okay, and when you go further down, you have a thermal properties of each material. Can you see the resistance?
Yeah.
0.037 meter square Kelvin per patch. So this is a resistance.
Mm. These resistant values actually they will give, right, the
Yeah, the
supplier or whatever
architect.
material.
No, basically architect because architect is designing the material, right?
Mm. So like whoever we are going to procure, sorry, what do you call it? Architect will give. Okay, at that time, at that stage, we don't have any procurement.
Yes, 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 yes. See here also they have given when resistance is not available, you can also use that equation R equal to S by K. K is nothing but conductivity of the material, right?
Mm.
So you can also calculate R by using the
Okay.
conductivity
Mm.
when resistance is
Just
not
like
available.
when resistance. Okay.
Clear? Okay. Now we
Yeah.
go further down. This is the basic thermal heat transfer equation. Q equal to mCp delta T, right?
Okay, main equation. Delta
Yeah.
T.
So
Yeah.
M is nothing but mass of the material.
Mass
If
of
you
the
expand
material.
further, it is nothing but volume of particular material. Okay. It may be
Mm.
liquid or maybe gas or maybe water
Mm.
or air, right? Multiply
Yeah.
by density. What is the density? Each material have a different density, right?
Yeah.
Okay. Then
Yes.
specific heat. Have you seen specific heat? I sent you one video.
Yeah. Yeah. It is the amount of heat required to raise the temperature by 1 degree.
Yeah, yes. Jeffrey also seen that video.
Yes, sir. Yes, sir.
Yeah, so whatever I'm sending you the video, it's all basic, huh? Because that basic will give
Yeah.
you more,
Idea.
the more idea, right? Okay.
Mm.
Next one, delta T, temperature change in the material. Okay, say for example, when you see the thermal resistance outside and inside, the what is the temperature outside
Temperature
and what is
difference.
the temperature inside, and what is the delta T, right? And I sent
Mm.
you one lecture, US from US. There was one old man. He took the lecture. Have you seen that video?
I think I saw that, but I can't remember. An old man taking video. I think I saw that. I don't know. Like I forgot. Maybe long back.
Okay. No, I recently I shared that video
So in the group,
in the group. Yes, yes. Let me share it once again.
I saw one lecture, but I don't know if it's the same.
Yeah, that is the introduction to heat transfer, conduction, convection, radiation. How that equation? Okay. How that
Okay.
equation came? That is also there. I'm sharing you that video too. Okay. This will give you again the basic idea. Okay, so if you go further down, you have outdoor design condition that I told you already before that based on the Ashray conditions. Okay, so this is the chart you have to refer based on the Ashray climatic condition, right? And this is the indoor design condition as per Ashray requirement. If it is office, conference rooms, what is the temperature required in the during the winter and during the summer? Okay, for the human comfort, right?
Yeah.
Okay. Then for the roof load calculations, how you calculate Q equal to UA right? Cooling load temperature difference. So this equation came from where?
MCP delta T. Same.
Yeah, that's okay. But this based on which standard? Have you seen chapter 17?
Yeah, that we have this RH, what do you call two methods were there. I forgot.
No, in the chapter 17, there is one equation, right? Q equal to UA CLTD, right?
Cooling load
So,
temperature difference.
yeah, so this came from Ashley fundamental, right?
Okay.
Okay, how this equation came, that I sent you one video. If you watch that video, you will understand how this equation came, right?
Okay, sir.
Okay, U is nothing
How
but
you said?
U factor, and A is nothing but area, and CLTD, cooling load temperature difference. Okay, this equation, how it came, that video already given to you. Okay, and there is a wall load, it's the same, Q equal UA CLTD, right?
Yes, sir.
Okay, then window load, glass conduction. This is a conduction heat, right? So the same equation, Q equal to UA CLTD. So whenever you have a conduction, you will use this equation, right?
Okay, sir.
Okay, then
Conduction.
yeah, this is for the U factor for various fenestration products. Okay, you have a different product having different U values, right? Okay, this also based on Ashley fundamental. Okay, and if you go, this is based on the window load. Okay, so what is the equation? Q equal area of the window multiplied by
Glazing
shading
factor.
coefficient multiplied by solar cooling load factor multiplied by cooling load factor. This is the equation to calculate the heat. Okay, so this equation came from by using this one, right? There is a glass and there is a heat will be transferred from one side to another side. Okay, through the thickness of the glass. Okay, so that is why you have a area of the glass. Then you have a shading coefficient. Okay, how much shade? Okay, then you have a solar cooling load factor, and then you have a cooling load factor CLF. So by using this equation, you can able to calculate the Q heat, how much heat
This
through
shading coefficient, SGF, this solar cooling load factor, like where we get these values.
see cooling load factor you just assume as a 1. Okay, this also value will be given by your glass vendor. Okay,
Shading
and
coefficient will be given.
yeah, shading coefficient is nothing but how much shaded. Remember when you see the if you travel by car, if you ask for the window, okay, if you go for the window, that for the screening, right? They will say that they will tinting. Yeah, they will ask how much percentage, how much shading, right?
Okay.
Okay, if you have a clear window, if you sit inside, okay, in the car, and if you have a clear window, the heat will be more or less. More, right? And if you put a
Yeah.
tinted, that means shading. Okay, if you increase the shading, what will happen?
Somewhat cooler.
Yeah, somewhat cooler, right? So that is the shading coefficient. How much percentage shading coefficient?
Ah.
If it is a clear, then you will get a more heat. So that is also a matter, right? Okay.
Okay. Solar cooling load factor 1. Huh?
Yeah, as of now, you just consider as a 1 because it's a safety factor, like cooling load factor. Okay, it's nothing but
Cooling load
CLF also the same. CLF also the cooling load factor is both are same. Okay, this watts per meter square, right? Okay. When you go further down, this is cooling load estimation through the partition and floors, right? So what is the equation? Q equal UA delta T.
Equation.
Yeah. U is nothing but design transfer coefficient, area calculated from building plans, and temperature difference from adjacent space to the room temperature, design temperature, right? Okay.
Yeah.
And if you go further, for the occupancy, you have a both sensible load and latent load, right? Okay, this equation came from where again?
Which one, sir?
This equation.
Sensible NFD, number of people, diversity factor, sensible heat gain, cooling load factor. This conduction equation.
Yeah, same. It came from your Ashley fundamental.
Okay.
Okay, so all the equation, whatever the equation here, it came from Ashley fundamental chapter 17. Okay, 2021 chapter 17, right? This is sensible and also this is a latent load. So whatever we are studying here is as per Ashley fundamental.
Fundamental, okay.
Okay, then heat gained from people. This also from Ashley fundamental. Okay, how much depends upon the activity, what is the sensible load and what is the latent load from the human. Okay, and this is a lighting load. And lighting load, this is also equation available in Ashley chapter 17. Input what from electrical plants, lighting use factor, lighting special allowance factor, cooling load factor. Okay, based on the hours and operation. Right?
Okay, sir.
Okay, then you have appliance sensible load. You have appliance, you have a sensible. If you have appliance based on the latent, okay, there is the equation. Then you have a latent load from motors.
Motors.
Then you have a infiltration. Again, this is as per ASHRAE. Okay, ASHRAE fundamental infiltration. You have a two method: air change method, effective leakage area method.
This one nice.
Infiltration, you have a sensible and you have a latent, right? I will be sending you video for this as well to understand what is infiltration load. Okay.
Okay, sir.
Then what is a ventilation load? Ventilation load also you have a sensible and you have a latent, right? So this is a sensible equation. This is a latent equation. For sensible load equation, you need a temperature difference, and for latent load, you need a moisture difference.
Moisture difference.
Yeah. So this is a calculation, right? Okay. So when you go to your HAP thermal load calculation, okay, you can see that there is a weather properties. This is based on ASHRAE climatic condition, and this is based on the space. When you go to the space, you have general, internal, walls, roof, infiltration, floor, and partition, right?
Okay.
Okay. Now I am going just above. Say for example, okay. Now this is the cooling load from partition, right? So what is the equation? UA delta T, correct?
Temperature difference.
Okay. If I go to my calculator, HAP thermal load calculations, partition. So what I have here, area, right? And I have a U value here. And can I see the temperature difference?
Yeah. Unconditioned space.
Yeah. So this is unconditioned space maximum temperature and ambient space at maximum temperature. Okay. And what is the design condition? That will take from the system. What is the design temperature, right? So that is the temperature difference. That is the temperature difference.
Okay.
So this is the ambient temperature, adjacent spaces, and this is the design temperature. So this you can get the delta T. Okay. So the same equation, whenever you are working in the HAP software, it is going to apply the same equation.
The same algorithm.
Yeah, same algorithm, right? So here you have a area, you have a U value, then you have a temperature difference from internal and external. Based on that, it will calculate what is the Q, right? Okay. If I go further up, say for example, I have a roof load, right? Roof load is what? Q equal to UA CLTD. Okay. If I go to the roof, this is the area, and this is the U value, right? From here, I will enter the U value here. So this is nothing but U, this is nothing but A, and the temperature difference from outside to inside. What is inside temperature difference? I have based on the system condition. Based on the system condition. So system condition I will apply here, right? This is my thermostat. What is the setting I am going to do? So this is my inside condition, right? And what is and my outside condition will be from the weather, based on the weather, right? So this is a temperature difference. So I have a delta T, okay, and I have a U and I have a area. So UA delta T, correct?
Yeah.
Okay. Now if I go to my result, okay, if I go to my result, okay, if I go to result, can you see that in this table, can you see what is a sensible load and what is a latent load, right? And can you see here wall transmission, roof transmission, window transmission, skylight, door load, floor transmission, partition, ceiling, overhead lighting, task lighting, electric lighting, people, infiltration, right? So whatever we have seen here, this is a zone load, okay? And zone load consists of both. You have a sensible load and latent load, right? Okay, so this all value came from where? By using that equation, correct?
Yeah,
so when you add together, you will get total load. Total load is nothing but what? Sensible load plus latent load. Okay, so if you go further up, okay, if you see the result, okay, can you see this result here? Total cooling load this much, and sensible load this much, airflow rate this much, right? and your entering temperature, leaving temperature, your outside temperature, and what is the bypass factor, okay, and what will be the chilled water flow rate, everything will give you the result. Okay, you have any query?
This thing like how we are determining this chill water flow rate here? Like any other?
Okay, no, chilled water flow rate, there is the equation. Chilled water flow rate, there is all equation only. You are going to study all the equations, right? Okay,
Yes, sir.
chilled water flow rate, what is the equation here? Basically, I told you that Q equal mCp delta T, right?
Yeah.
Okay, what is Q?
Q is the rate of heat transfer.
Yeah, total heat, right?
No, sorry.
Okay, what is M? M is nothing but mass flow rate of water. Can I say like that? Okay,
Mass
okay,
of
what? Okay, how you will expand mass flow rate of water?
Density into volume.
Volume of water into density, right? Density of water. Okay,
Yeah.
okay, and what is that CP?
Sorry?
What is that CP? What is that CP?
Specific heat capacity of water.
Water. Okay, multiply by delta T, right?
Yeah.
And what is the delta T? Your chilled water coil temperature, right?
Okay.
So you know that chilled water coil having supply temperature and return temperature. So that is a delta T.
Yeah.
Okay, but from here, can you calculate your volume?
Volume?
Yeah, by using this equation, can you calculate volume?
Yeah, we can calculate.
Yes, you know the heat. You know the chilled water on and off coil, the chilled water supply temperature, return temperature, and you know what is the specific heat. You know what is the density of water. By using this
we have to
equation, you can
rearrange the
calculate.
equation.
Yeah, rearrange the equation to calculate the water flow rate.
Okay.
Okay, and also the same thing for air flow rate. What is the equation? Same equation. What is that equation? Q equal to mCp delta T. Okay, Q is nothing but heat. Mass, nothing but mass of the air, right? And you have volume of air multiplied by density of air. Multiplied by specific heat of air. Multiplied by delta T, temperature difference. What is the temperature difference? Outside air to inside air, right? Okay, so from here you can calculate the volume of the air.
Yes, sir.
So that is the
coil temperature. How we will determine that coil in inlet temperature?
inlet temperature and outlet temperature, right? For thermal comfort, based on the standard ASHRAE, the supply temperature should be like 5 degrees Celsius or 6 degrees Celsius, and return temperature should be 12 degrees Celsius or 13 degrees Celsius. Okay.
Okay. That normally we follow. Okay.
Yeah, that is a normal. That is a supply temperature and return temperature. Okay. Clear, right?
Yeah.
So that is a delta T from the water side, and from the air side that is a delta T. So that you can calculate volume rate for the air, and also you can calculate volumetric rate for the water by using this Q equal to mCp delta T equation. Clear?
Yes, sir.
Okay. Yeah, Jeffrey, you have any query?
Not right now, sir.